Okay, we're on chapter 4 today. 4.1 and 4.2. Page 190 is where we start. And the first thing you want to do is start a page of notes for chapter 4 and put on your notes Egyptian numerals. Egyptian numerals. And there they are. I don't know if I've got all the names right or not. Where do they tell us? There it is. A stick. No, a stroke. I'm sorry, page 184. A stroke is 1. A heel bone is 2. A scroll is a heel bone is 10. A scroll is 100. It's on page 184. A lotus flower is 1,000, and a pointing finger is 10,000. Now they give more than that on here. They give 100,000 and 1,000,000, but none of the problems have you go that far. So these are all the numerals you need to work the problems in this chapter. And those will be enough numerals to get you through the test. So, problem number 4. On page 190, says write this numeral in Egyptian notation. And the number is 1,247. So what do I do for 1,000? I put a lotus flower. What do I do for 200? Maybe I should just mark this out like this. Here's 1,000. What do I do for 200? I put 2 scrolls. What do I do for 40? I put 4 heel bones. And what do I do for 7? I put 7 strokes. Is that what they call them? Everybody follow that? So now you know how to take a number, a numeral, and translate it into Egyptian numeration. How come I did 2 of them? Oh, no, this is different. Now, number 8, they give me an Egyptian numeral and tell me to translate it into decimal notation. So, what's a lotus flower?
1,000.
So there's my 1,000. How many scrolls do I have? 9. So there's where my 900 comes from. I don't have any heel bones because I don't have any 10s, but I have 1, 2, 3, 4 ones, so that's where my 4 comes from. Okay? You got this down? So we're ready to go to number 14. What do we do on 14? Write each number in Egyptian notation. And perform the indicated operation. So I have 148 plus 45. So I put 100, 4 heel bones, and 8, and 4 heel bones and 5, and then I just add them together. And I'm going to be thinking in decimal. I can't help that. So I bring down my 100. I have 1, 2, 3, 4, 5, 6, 7, 8. So that's where I get 80. But then I just write 1, 2, 3, 4, 5, 6, 7, 8. Then over here, I add this up, and I get 13. But I can't say 13 in Egyptian. I have to say 10 and 3 strokes. You follow that? So that ends up giving me an answer that's a scroll and 9 heel bones, which would be the 90, and 3 strokes. And if I was doing subtraction with this, if I would have been doing subtraction, I would just take the 1, 2, 3, 4, 5, 6, 7, 8, subtract 1, 2, 3, 4, 5, and I would end up with 3. If this was a subtraction problem, I would have 3 strokes. I have 1, 2, 3, 4, minus 1, 2, 3, 4. I have no heel bones and a scroll. You see how that would play out if I was subtracting? All right. So now we're ready for the fun part of Egyptian mathematics. Should have told you to bring some M&Ms today. Some of you aren't going to like this. But can you tell by the name? Successive duplications. Is that what it says? Yep. Successive duplications. I'm taking 25 times 15. So I start out with 1 times 15. Let me erase this here. Getting ahead of ourselves a little bit here. Why is that not working? Yeah, I'll erase all this too. So I start out writing 1 times 15. You see that? And then, well, I'll put it over here. 1 times 15 is 15. 2 times 15 is 30. Now, you don't go to 3 times 15. You go to 4. Duplications, doublings. 4 times 15 is just double 30 to 60. 8, from 4 I double it to 8. 8 times 15 is double 60, 120. See why they call it successive duplications? And then I go to 16 because I've doubled 8, and 120 doubled is 240, and then 32 is 16 doubled, and 240 doubled is 480. You follow why we call it successive duplication? I'm just making for each problem for this successive duplication thing, I just make a table. And then, how do I find the answer? Okay, now here's where it gets interesting. And here's what it says to do. Oh, we don't have the instructions on this page. They're back on page 185. Look back there and see what it says. Does it say? Well, here's what happens. I need 25 of these 15s. So here's 32 15s. You follow me? Here's 32 15s. That's more than I need. Here's 16 15s. Okay? But that's not 25, but that's getting close. So what would you add to 16 to get 25? You won't, right? So what do I add to 16? I add 8, and what does that give me? What's 16 plus 8?
24.
So I just need one more. See where I get my 25? So now, what's the answer? 15, this one, plus 120, plus 240. 5, 7, 375. See how that works? You go, that is so dumb. Why didn't they just get their calculator out and punch in the digits? They didn't have calculators. And if you think about it, if when you first were taught multiplication to multiply 25 times 15, where we put one under the other and multiply and carry and da da da, and then add the answers when you're finished, this is not a bad way to do multiplication. It's just, no, I've never done it that way, and I know another way to do it, so it bothers me to learn somebody else's way of doing multiplication. Okay, you got that down? Any questions on how to do successive duplications? Because the test will ask you to multiply by successive duplications. Or it'll have part of the process, and it probably what on the test it'll say is, if it was 25 times 15, it'll say, so which rows do you multiply, or which rows do you add to get the answer to 25 times 15? And you would say the 16, the 8, and the 1 row. You follow that? Because they want you to know this process. So put this process in your notes. Then somebody decided there was more than one way to do multiplication in Egyptian, and so they went to, in fact, I think what somebody thought was, this is really faster than making that table every time. This is called mediation and duplation. Now, you can see duplation sounds like doubling, which is what goes on over here. 32, 64, 128, 256. Mediation might be a little strange, but mediation, let me just erase all this. Mediation says 15, divide 15 by 2, and what do you get? 7, remainder 1, forget about the remainders. You don't need them. 7 divided by 2 is 3, remainder 1, forget about the remainder. You don't need it. 3 divided by 2 is 1. So now I've taken 15 by dividing by 2 all the way down to 1. And you say, yeah, but you have a remainder. Don't worry about remainders. Just discard them. So now I want to find the answer. And the way you find the answer is add up the odd numbers. Well, this is odd, this is odd, this is odd, and this is odd. So that means I add 32, 64, 128, and 256. And what do I get? 20 and 18 and 480. Is that right? Is that 15 times 32? I don't know. Let's get our modern technology out here and check it out. $15 times 32. 480. Good. All right. Number 24. Let's do another one. Since these are a little tricky. 40 times 61. So I have 40 and 61. Then I go 20 and double 61, 122. Let's just do one column. 61, 122, 244, 488, 976, 1,952. You see what I'm doing? I'm just doubling the ones on the right. Then the ones on the left, I'm dividing by 2. 40 by 2 is 20, 20 by 2 is 10, 10 by 2 is 5, 5 by 2 is 2, throw out the remainder, 2 divided by 2 is 1, and I pick what? The odd ones. So here's an odd one, here's an odd one, and the rest of them are even. So what do I add together? 488 and 1,952, and I get 2,440. Let's check that one out. 40 times 61. 2,440. You follow the process? The trick to this is what? Make sure that after you've done your doubling on the right-hand side and your halving on the other side, that when you get to the answer, you take the odd digits, the odd numbers on the duplation side. I mean on the mediation side, on the halving side. All right. Got that down? Let's do some Babylonian notation. What do Babylonians have? Do they have names for those? I don't know if they do or not. Doesn't look like it. Axe head, airplane. That's about it. An axe head is 1, an airplane is 10. And what's this? Okay, an axe head is 1, an airplane is 10. An axe head with a space after it is 60. And an axe head with 2 spaces after it is 3,600. You go, what? You know how our system is based on tens, so we have ones, tens, hundreds, thousands, 10,000s. Well, the Babylonians listened to their heart. The heart beats about 60 beats a minute. So they based their math system on their heartbeat. I don't know if that's really true. It just makes for a good story. So 60 is the number they're working with. So you say, how do you go from 10 to 60? You just fly there in your little airplane. But see, it is, and now the book is kind of deceiving because it shows these. The book shows the 1 is a little axe head, and the 60 is a big one, and that's not necessarily, that's not the way it was. The axe head's the same size. It's the space afterwards. And you'll probably find when we start doing some of these problems that looking at that space, you're not going to see it because your eye's not trained to see that. Your eye is trained to see a 0, but they didn't have a 0, so they just left a space there. So I'll show you when we get there what it does here, how it messes with your head. But this is the Babylonian notation, and you want to put that in your notes. And I'll show you why. Because 26 says, rewrite 24, the number 24, in Babylonian. So that would be 2 tens, 2 airplanes. What are those things that fly out of Whiteman that sneak up on you and you can't even hear them coming? And 4 axe heads. You follow that? So what about problem 30? 144. Now, watch what happens here. Okay, I don't have 3,600, but I do have 60. How many 60s in 144? 2 times 60 is 120. Let me erase this for a minute. 2 times 60 is 120. Everybody see that? So I put 2 60s here. And there's that empty space. In my textbook, when I'm over here working problems 35 to 40, I actually took my pencil and drew little circles in those empty spaces because my head mathematically doesn't have a place for an empty space meaning something. So I just in my book wrote zeros in there so you could see what was going on. And since we're looking at them, problem number 40 in your book, you say, it doesn't look like there's 2 spaces between the first one and the second one, But if you have digits and a space, and then digits and a space, can you see where the first space would have to be 3600s and the second one would be 60s? So you have to kind of develop a Babylonian mindset, which you won't because we don't do enough exercises. So just write yourself some notes to see what's going on. Okay, problem 30. Let's finish that one. 120 from that leaves 24. So that means I need 2 10s, 2 of those airplanes, and 4 axe heads to get 24. You follow the process? Then let's do problem 34. 3,883. Well, let's keep our digits up here where we can see them. Okay? So I can subtract 3,600 and put an axe head here with 2 spaces after it. See that? Even though if you look at a Babylonian tablet, it would only be about 1 space in there. It doesn't matter if you stretch them out a little bit to make 2 of them, just to help our minds wrap our minds around this concept. So after I do that, I have 283 left. So how do I say 283? Let's see. 60s. How many 60s in 283? 4 of them. 4 60s is 240. So I subtract 240. So that means I have to have 1, 2, 3, 4, followed by a space to represent 60s. See the process? Because I have to have 4 60s to get my 240. And that, you say, why didn't you use 5 60s? Because what would 5 60s be? 300, and that would be too much. That would be more than 283. So I'm using as many 60s as I can. So then I'm left with 43. So how do I say 43 in Babylonian? 10, 20, 30, 40, 1, 2, 3. You follow the process? Write enough notes. See, here's the sad thing about this book. It doesn't give you enough practice for you to absorb this information in your head. So if you don't have notes where you write down some stuff on how to do it, when it comes time to do it on the test, you'll probably forget. Because this little time we talk about it here in class isn't going to make it stick permanently for the rest of your life. So that means you just need good notes. Okay, now we're ready for problem 36. Now, do you have those symbols in your notes that I gave you, those Babylonian symbols and what they're worth? Because it's off the screen now, so you can't see it, but that's okay. We know it now, don't we? Well, we'll see if we know it. Number 36 has one of these things, which is 10, and this is 1, 1, 1, so that would be 13. You follow me? But it's 13 what, since there's a space here? 13 60s. So what's 13 times 60? Well, here we go again. 13 times 60, modern technology, 780. Then we come over here and we say, I've got another 10 and then 2 1s. And that would be 12. So what's 780 plus 12? 792. See what's going on? Do you like Babylonian numeration? Let's do number 40. Yeah, number 40. That looks like fun. Okay, watch what number 40 has. It has 2 axe heads, 2 for 3,600. Because see, I've got these 2 spaces and then this space here. So these are the 3,600s and these are the 60s And these are the tens and ones over here. But I don't have any tens, I just have ones. So I have two of these 3600s, that's 7200. 10 and 1, that's 1160s, that's 660. And then 1, 2, 3, 4 ones. That adds up to 7,864. Do you like Babylonian numeration? Well, skip problems 41 to 43.
When you look in the book, how are you supposed to tell the spacing?
That there's a space there?
It all looks the same.
How do you tell if there's one or two spaces?
Okay, look at number 35. Do you see a space in problem 35?
Yeah.
So put a little pencil circle there. Look at number 37. Do you see a space in number 37? Now look at number 39. Do you see any spaces in 39?
There's two spaces.
There's two spaces. You see that? There's two spaces in 39? Do you see it?
Will there ever be two spaces right next to each other?
No. There's two spaces. See, that's why I put two spaces here, just to kind of make sense out of it to us. But there's a space between the axe head and the airplane. Do you see that? For 39. And then there's another space at the end between two axe heads. You see two axe heads, a space, and two more axe heads. Do you see that? Yes or no? Okay, so if I have two spaces in a numeral, then the one closest to the tens and ones is going to be 60s. What's the next space going to be? It can't be 60s again. It has to be the next place value in my numeration system. So it jumps up to 3600. You follow the rationale? The book won't separate it to make a double wide space. It'll just say, hey, if there's two spaces in a numeral, then the first space, the numeral to the left is 3600, and the next space, the numeral left of that, right left of that, is 60s. Okay? Skip 41 and 43 and go down to Roman numerals. We like Roman numerals, don't we? And you know what? You say, oh, I've seen Roman numerals. Okay, I have too. You say, so I'll be okay doing these. Well, you better put this in your notes too. Because it might be you haven't had enough experience with Roman numerals to be able to do some of this stuff that they want you to do here. And what is that? Number 46. Change that Roman numeral to a decimal numeral. What's D? $500. What's C? 100. And what's XVII? XVII. What would that be? 17. So what is it? 617. So let's do number 48. What's XXX with a line over the top? You go, I don't know. What's a line over the top mean? Right there. CV would be 105,000. The line over the top says this is CV is 105. Take that times 1,000. Or we could change that to, just for fun, CL, and that would change it to what? What's CL? 150, so that would change it to 150,000. You follow the process? Okay, so number 48, those three X's with a line over it is 10, 20, 30. So that, back to red, that's 30,000. And then what's D? 500, C? 100, 600, and 1. So 30,601. Number 50. What's number 50 say? LDDC. But the LD has a line over it. So LD, back up to my chart. What happens when I put 50 in front of 500? You subtract the 50 from the 500. So that becomes 450,000. You remember that? You say no, then write that down. If you see a smaller Roman digit in front of a larger Roman digit, that means you subtract the smaller one from the larger one. Like, how would you say 9 in Roman numerals? V-I-I-I-I? No, you would say I-X. X minus the 1 in front of it. You say, well, couldn't you say V-I-I-I-I? Well, you and I would understand it, but a Roman would look at that and say, that's bad penmanship. That's not the way we write it. So you kind of have to get the drift of what Romans are thinking when they're doing their mathematics. And I think since the Romans were into beauty, they probably said V-I-I-I-I isn't as beautiful as I-X. And I would agree with it. Okay, so number 50, we have 450,000, but then we have D, which is 500, and C, which is 100, so we have 600. So it's 450,000 and 600. I did a couple of others over here just for fun, because I didn't think they gave you enough practice. CD would be 400, and XL would be 40, so that would be 440. See how here's the L, 50, X is in front of it, so I subtract the 10 from the 50. And CD, I have 500 minus the 100. Okay, that's probably enough of that. Let's jump down here and do problem 52. Yeah, why did I write it so close together? So we could keep the numbers on the screen and look at them. Problems 52, 631. Write that in Roman numerals. Well, how would I say 600? 500 and 100. So that would be a D followed by a C. Everybody see that? There's my 600. How would I say 31? 10, 20, 30, followed by a 1. Everybody follow what's going on? 54. How would I say 1,709? Well, for 1,000, I would just have M. For 700, I would have 500 and 2 100s. So that would be a D and 2 C's. You follow the thinking? So there's my 700. And then 9 would just be IX. 56. We can't see them. Well, try to remember them. Or look at your notes if you've written them down. 56. 49,231. Well, 1,000, there's 49. So I put, here's 49. You go, what? Yeah, XL is 40 and IX is 9. You say, why can't you just write IX? It doesn't look right. Makes a Roman feel bad. So XLIX with a line over it to make it thousands. And then 200s, There they are right there, CC, and 30, 1, 2, 3, 1. All right. Stop at 55 and turn over to page 197. Writing numerals in expanded notation. Have you done this before anywhere in life? Problem 2 on page 197. 500, so I go 5 times 100. 4 tens, so I go 4 times 10. And 9 ones, so I go 9 times 1. Except the way this math book wants you to write that is 5 times 10 to the second, because 10 squared is 100, 4 times 10 to the first, and 9 times 10 to the 0. So this is the way you need to write your answers for this book here. Learn to write them in terms of exponents. That's so much prettier than just strung out like that. So let's go to number 6. 1 10,000, 0 thousands, 9 hundreds, 5 tens, and 0 ones. You follow what I did? Expanding this thing out. So that's 1 times 10 to the 4th. And a shortcut for that is because there's 1, 2, 3, 4 zeros. 0 times 10 to the 3rd, because there's 1, 2, 3 zeros. 9 times 10 to the 2nd, 2 zeros. And 1 and 5 times 10 to the 1st, 1 0. And then 0 times 10 to the 0. Do we all know that 10 to the 0 equals 1? Just put that in your notes if you didn't know that already. Any number to the 0 power equals 1. So here's my answer for number 6, but here's what the answer book shows. This is the keyed answer. 1 times 10 to the 4th, plus 9 times 10 to the 2nd, plus 5 times 10. What did they leave out? All of those zeros. See that? Because, whoops, you don't need those. You don't need those zeros in there, because 0 times 10 to the 3rd is nothing. So they're saying if it's nothing, then I don't have to write it. But I write it when I'm translating, so I don't lose track of the place values. Like problem number 8. What's problem number 8 say? Write this in decimal form. 3 times 10 to the 1st plus 4 times 10 to the 0. That would be the tens place. A 3 and a 4, that would be 34. Number 12. Turn the page. 7 times 10 to the 4th plus 2 times 10 to the 0. Now see, what's left out is the 3rd and the 2nd. So to make sure I don't lose something, I put 7 times 10 to the 4th plus 0 times 10 to the 3rd plus 0 times 10 to the 2nd plus 0 times 10 to the 1st plus 2 times 10 to the 0. And what that does is that gives me all of my places in there. So the answer is 70,002. See, you probably aren't familiar enough with expanded notation to take care of those zeros in your head. So I just write them on the paper to make sure I don't overlook a place value. And then we put zeros in those place values. Number 14. It's got 10 to the 9th, and then 10 to the 5th, and 10 to the 2nd, and 10 to the 0 power. So I just had 8 times 10 to the 9th, and then 0 here, and 0 here, and 0 here, until I work my way down to 3 times 10 to the 5th, and which means I'm going to put zeros in there when I get my final answer, and 0 here, and 0 here, and 2 times 10 to the second, and 0 here, and 4. So what's my final answer? 8 billion, no million, 300,000, 204. And can you see on the test, when he puts one there and say which of these decimal numerals matches this Roman numeral, or matches this expanded notation, can you see where he's going to put some choices there where you can overlook some of those zeros? So you might just copy down this process to keep it handy. Skip problems 16 through 22. I just want you to understand expanded notation. You don't have to add and subtract with it. But do you remember studying exponents somewhere? That's the next section here. Exponential numbers. Okay, put this in your notes. X to the m times x to the n equals x to the m plus n. What does that mean? 6 to the third times 6 to the fourth equals 6 to the seventh. X to the m divided by x to the n. 6 to the third divided by 6 to the second equals 6 to the first. Sometimes when you're putting down these generalized principles in letters, it doesn't hurt to write an example next to it. 5 to the fourth times 5 to the third would equal 5 to the seventh. You follow that? 4 to the sixth divided by 4 to the second would equal 4 to the fourth. Everybody see what's going on? And then over here, 5 to the fourth to the third power would equal 5 to the 12th. In other words, just when you're looking at these principles, you're saying, you know, those letters confuse me. Then make up a sample problem and stick it right there with the generalized formula, so to speak, so it makes sense in your own mind. And then any number to the 0 power is 1. 5 to the 0, 4 to the 0, 3 to the 0. And if you want to know why, stay around after class and I'll show you. I used to take class time and say, who wants to know why? And nobody would raise their hand. So I say, okay, for those who want to know why, just talk to me later and I'll show you. It's really fun figuring out why. But if you're agonizing over some of these rules, then it probably would help to stay after class and have me explain to you why the rule works to help it stick in your mind. Problem 24 says 3 to the 5th times 3 to the 9th. Well, you add the 5 and the 9 and you get 14. Now, maybe you're thinking, can I take 3 to the 5th times 4 to the 9th? No, it has to be the same base before you can follow this rule. And I did a little expansion here just to show you why that works. Number 30, 7 to the 15th divided by 7 to the 3rd. Now, what does your little heart want to do when you see 7 to the 15th divided by? You want to divide 15 by 3 and get 5, right? And that will be one of the choices on the test because he wants to catch you doing that. No, it's subtract. So the answer is 15 minus 3 is 12. When you're dividing exponential numbers, you subtract the exponents. When you multiply exponential numbers, you add the exponents. When you have an exponential number to an exponent, you multiply the exponents. So that's 3 times 5 is 15. Skip 36 to 42, and let's do some story problems. Number 44. You know the drill, don't you? You know my process. I try to minimize the words and just extract the math facts from these sentences. So what do I have here? Each American, 4 pounds a day. I don't even care what it is they're doing. I'm just extracting the math. The population is 2.9 times 10 to the 8th. Total per day. For the whole population, that means I take 4 times 2.9 times 10 to the 8th. Now, you know what's crazy about this? If your answers don't match when you start working some of these problems, see, here it says the population is 2.9 times 10 to the 8th. Look what it says between problems 50 and 51. In problems 51 to 60, assume that the population is 2.8 times 10 to the 8th. And in the answer key, sometimes they use 2.9 times 10 to the 8th. So they're changing numbers on you. And I don't know if that's just a misprint in the book, but don't get stressed about it. Just say, hey, they keep changing the numbers. And then sometimes in working 51 through 60, at least the answer key for the even problem said they were using 2.9 instead of 2.8. So don't let that get to you. But what's 4 times 2.9? 11.6. But now, see, you probably don't know this, but 11.6 times 10 to the 8th is just not appropriate. I need a number that's between 1 and 10. Or between 1 and 10 or 1 and 9 inclusive. So that means I changed my 11 to 1.16 times 10. Because what's 1.16 times 10? 11.6. So now if I have 10 to the first times 10 to the 8th, then what does that give me? 10 to the 9th. So now my answer is 1.16 times 10 to the 9th. Number 46. What's 46 say? Americans use 3 times 10 to the 7th gallons of motor oil every day. So we use, maybe I should have put that in here, this much gallons every day. How much every week? Well, that would just be 7 times this number. 7 times 3 is 21, but I don't use 21. I change it to 2.1 times 10 to the first, and then add the 1 and the 7, and I end up with 2.1 times 10 to the 8th. You follow that process? Number 48. Americans discard 72. Now, see, they shouldn't have written that. I don't know if that's a misprint, whether they meant 7.2, so who knows what's going to happen when you check your answer on some of these. But since it said 72, I'm using it. They discard this much each year, so how much each month? So I just divide this number by 12. And that would be 72 by 12 is 6 times 10 to the 7. So that's how many batteries are discarded every month. Number 50. Each day, they discard this much each year. Each day, divide by 360, which is 3.6 times 10 to the second. So I come here and do my division, and I end up with 2 times 10 to the 5th, subtracting exponents for division, and 7.2 divided by 3.6, get your calculator out and you'll find out it's 2. Okay. 52, we consume 5.96 times 10 to the second pounds per person each year. How much total for the population each year? And the population, it said, used 2.8. But the keyed answer in my book used 2.9 times 10 to the 8th. Same number they had over on problem 44. So if your answer doesn't match exactly, don't assume you did it wrong. Number 54, that's total each person a year. We've done one of those. Number 56. Oh, we have to do number 56. Yeah. 56 is so much fun. No, it's 58. That's the one I want to work. Yeah, let's do 58. Oil reserve. Excuse me. This book was published in 2005. So, 14 years ago. I don't know if the guy got on the internet to find out, but he said, we're in trouble. We only have 3.5 times 10 to the 10th barrels of oil in the ground, and we're pumping that stuff out at 3.2 times 10 to the 9th every year. How long will our oil reserves last? And the answer is 10 years, 11 years, which means by 2016 we should have run out of oil. And if we would have, then you all would be driving pedal cars or bicycles or finding another way to get around. Leave early enough to walk to school. Or we'd have tons of public transportation. We'd be driving little solar cars. Who knows what we'd be driving. But why didn't we run out of oil? Because, you know what's happened since 2005 to today? In fact, I just read, probably last month, that some guy went up into Alaska and found a whole new reservoir of oil underground that's bigger than the oil they discovered in Texas years ago. And in South America, they've been discovering oil. So this thing about oil reserves, we've been discovering oil reserves we didn't know existed 19 years ago. Now granted, someday it's going to run out, but don't worry about it. When the oil's all gone, we'll all figure out another way to get around. We'll just chuck our gas-burning cars and all be driving people-powered vehicles. What is that? Well, it's a bicycle, but a number of years ago, the Popular Science magazine had a picture of a people-powered vehicle that was streamlined, shaped like a bullet, and you sat down in a reclining position, and it showed a guy pedaling this thing, going about 50 miles an hour down the highway without working up a sweat because of the way it was geared for shifting gears. So you guys will figure it out. My generation, there's enough oil to last, so we keep driving our cars. Sorry about that, guys. You just have to deal with it. Problem number 60. Sun energy each minute. I thought this was interesting. It says it's 1.02 times 10 to the 19th, that's calories. Or I looked that up on the internet. Calories are also joules, which might not mean anything to you unless you've been in science class, but also BTUs, British thermal units. So, it's that stuff. And the Earth's surface is 5.1 times 10 to the 8th square kilometers. But a square kilometer is 10 to the 10th square centimeters. You know, a kilometer is a little bit less than a mile, and a centimeter is about the width of your tiny fingernail. So what happens is, I have to take 5.1 times 10 to the 18th to the 8th, so I add this 8 and this 10, and I end up with 5.1 times 10 to the 18th, and I divide the total 1.02 times 10 to the 19th to see how much I get, and it looks like there's about 2 calories or 2 British thermal units from the sun, a strike in each little centimeter of the earth. Is that per day? Each minute. Wow, each minute. How powerful. Problem 62 has you explain what you must do to divide a to the m by a to the n. And I said, subtract n from m, and then write it like this. And the keyed answer said, write a with the exponent m minus n. Well, that's a much better way to say it. It's just not the way I said it. But it means the same thing. You follow me? So don't check yourself wrong when you're working 61 and 63. And stop at 63. Okay? That's it. If you want to correct your test, it's laying up here on the table. Come and get it. And I'll help you work through it if you can't figure out what's going on.